All right, so today I have Alex Remedios. He is founder of Treebeardtech, which is a consulting company which equips machine learning teams with the reliable, secure, and flexible cloud architectures needed to deliver business-critical AI. So, Alex, welcome to the Data Exchange podcast.
Thanks, Ben. It's great to be here.
And we're going to talk about a bunch of things. But the first thing I wanted to talk to you about is this early warning system that you built in conjunction with Faculty.ai, one of the leading AI companies in the UK. And full disclosure, I am an advisor and investor to Faculty, so that's why I'm quite familiar with their work. So first of all, Alex, give us a background of what was the faculty system designed to do, and then we can go through the problems and solution.
Yeah, for sure. So background on the early warning system project. I'm sure similar to in the US, around sort of March 2020, it became pretty clear to the UK government and the UK national health system that the COVID pandemic was going to be arriving. And it wasn't actually obvious or clear if the country was ready to accommodate the increased need for hospital beds. So there were quite a few emergency meetings in early 2020 with tech companies, in the UK, but also from the US. And they started this initiative of trying to understand how many beds are occupied across all of the hospitals in the UK. And also thinking about things like mechanical ventilator beds, which would be necessary for patients that needed intensive care. And Faculty was one of the main companies that started to provide data science services and models for helping the NHS and very high levels of government understand the situation here.
And these are basically forecasting and forecasting models.
Yeah, exactly. They're Bayesian models that would operate on time series data and provide a range of possibilities of how the need for beds at each hospital might evolve over the next few weeks.
And so was this, would you consider this like a big data problem? Was there a lot of data involved, or so what were kind of the somewhat of the details in terms of the implementation?
Yeah, sure. Well, to give you an understanding of the context, in 2020, there was a lot of sort of data integration to be done. So, large public sector organizations, they often don't start to get their data all in one place until there is the possibility of providing AI services. And so they essentially found data sources throughout the UK. They were using Palantir's Foundry product to warehouse them, and then the models would essentially be pulling data down from Foundry and also accessing new data sources provided by Apple and Google, which, in the context of the pandemic, provided aggregate level details of how much people were traveling, and also there were other sources like how much people were calling the emergency phone lines, with COVID.
So this was both data fusion and real time, it sounds like.
It was real time in the sense that these data sources were updating on a daily basis because that was necessary for pushing the forecasts out every day.
And the Bayesian, to me, always connotes computationally intensive.
Yes, it was very computationally intensive in the sense that if you imagine there are over 100 NHS trusts in UK, each one needed their own forecast to determine, if London's need was greater than Manchester, for example. And this was done by running a algorithm called Markov chain Monte Carlo, which is a CPU intensive and inherently serial algorithm that essentially runs all night. So this is what was happening in parallel for hundreds of different models.
I am quite familiar with market-shaped Monte Carlo, having worked as a financial engineer for a few years. But okay, so then this models are in place. I imagine people would log on in the morning and see the readout from the model. So what was the technical problem where you came into the picture and where you brought along the open source project Ray?
Yeah, sure. So the infrastructure has gone through several stages of migration for the early warning system, starting with a single server to a single server with Airflow, and then to a Kubernetes cluster running Dagster. And it was at that point that faculty reached out to my company, Treebeardtech, to essentially understand why Dagster was experiencing failures. And these failures, which would sometimes occur, would cause the entire Kubernetes cluster to stop working. And this would impact all of the data science activities which were necessary for day-to-day operation and QA of the models.
And so Dagster, actually, I've had Nick here on the podcast. So Dagster, for our listeners, is basically a data orchestration tool, right?
Yes.
And then, where does Ray come into the picture, and why did you choose Ray? And
Sure.
For our audience, full disclosure, I'm also an advisor to Anyscale, the creators of Ray.
Cool. So to continue the story about Dagster, it was sometimes having these catastrophic failures within the Kubernetes cluster, and it was linked to the fact that apart from these daily, quite predictable but large jobs that we were running, there were also these less frequent development workflows, such as running extremely large grid searches. And Dagster has a number of different executors which you can use for actually running your workflow. And the one that was being used was called Celery Kates. And that means that every single operation in Dagster would create a Celery task. And then the task would create a Kubernetes job. And the Kubernetes job would use up disk space in the control plane. And the control plane was necessary for the entire infrastructure for the early warning system. So if you run too many tasks, you have too many Kubernetes objects on disk, and eventually the whole system would crash.
Right. And so then, were you already familiar with Ray at that point?
I was not. So, getting to the Ray part of this, it wasn't necessarily clear what the problem was or how we should approach it. And, we initially approached this by saying, we're going to fork the whole infrastructure and have a separate Dagster for running the risky stuff. Over time, it became clear that Dagster is a fantastic orchestrator, but it is not a parallel computing system with the same qualities of things like Ray, but more traditionally Spark, also Dask, and there are other frameworks like that as well.
Right. So why Ray?
Why Ray? Well, yeah, we got to the point where we said we can't use Dagster for all of this. We need to take the really parallel fan out that is running these models and have them using a different control plane. There's Spark, and Spark is tried and tested, but it has a JVM in the system, and that will always make it difficult to understand failures because, if you're running Python user code, Python user code fails, and then you've got a Java stack trace, and a Java stack trace has to go back through your Python driver process. The system is already extremely complex, from a data science perspective. There's also Dask, but Dask is a lot more data frame centric, and what we wanted was something really to just manipulate these MCMC based training processes. So I was looking at Ray, and I was thinking, this project's extremely well funded on GitHub. It was extremely active. You could see there were good reference customers using it. And also they just launched the Golang based KubeRay project. So their Kubernetes support was looking, pretty much as you would want it to be in terms of having a modern stack. So essentially, it was just the right fit for this use case.
Yeah. And I also love Spark because I'm an advisor to Databricks. So it's just that in this use case, there's no reason to bring in a JVM.
There's no reason to bring in a JVM. Save yourself the complexity, the memory usage, and make it easier for people to use. But also, understand that we're working in a cloud native setting, and my view is that the Spark ecosystem predates the cloud native movement, but Ray has sort of come of age with it. So I think that it's just it was always going to fit a bit better into the infrastructure.
And also, it sounds like based on what you're describing, right? So Ray has kind of the flexibility with actors and control and placement in the different nodes in your cluster and stuff like that. So once you brought Ray in, so what is the state of the early warning system today? Is it much more on solid footing, I imagine?
Yeah, I mean, so the major changes we made were we swapped the DAGs to executor to use a single machine. And, there are like in distributed systems, obviously people love to say horizontal scaling is the way to go, but vertical scaling as far as you can keeps things really simple. So most of the workloads we actually put back into a single VM using just a single multi-processing executor. And then for workloads that were doing like 1,000 core plus parallel fanouts, we hooked them up to a Ray cluster, and we're nowhere near the scaling limit there. So beforehand, we're dealing with outages and constantly facing sort of partial success where certain regions of the country would not get their forecasts on a given day due to random failures in the system. Ever since we moved to this model using Ray, it's been an order of magnitude more reliable.
All right, so then let's move on to our next topic, which is something I've been thinking a lot about. And by the way, before we actually do that, one quick pushback: Spark is actually being used by a lot of cloud native companies, including Databricks. So anyway, injecting software engineering rigor in how we build machine learning. So I was interested to see that you're actually also thinking about this. You even have an open source project along these lines for testing notebooks. So before we talk about the bigger topic of injecting software engineering rigor into ML, tell us about your nbmake project.
Yeah, sure. So apart from helping with machine learning, platform engineering through service engagements, we also just do open source platform technologies. And one of the main gaps we had a couple years back was that data scientists love developing initial prototypes, but also docs for libraries and basic scheduled workloads in notebooks. But they're kind of an odd format in terms of engineering processes. And we want to promote testing. We want to make sure that these systems are reliable, because before you even start interrogating a model's predictions, you need to trust that the system's actually being fit together properly. So we launched nbmake, and nbmake is widely used now throughout research and also industry by companies.
Describe a typical usage pattern. So I'm a data scientist, not a software engineer. I build a model which includes some data processing, some data manipulation, and then I build a model, I look at the results, but all in a notebook format. And since I'm a data scientist, I write documentation in the notebook also. So then what do I do then after that with regards to nbmake?
There's quite a few usage patterns, right? So a popular one is if you are working in a large company, you might be building a library that helps people, which allows teams to use like natural language processing features in their service. And in order for them to use your APIs, they need to have like a notebook environment that lets them prototype a model. So you might write your docs in a notebook, and those docs are essentially testable against your library. So
Oh, I
that's one use case where it's like an end-to-end test for a library.
Right,
Yeah.
right. But what about the one I described, which is I'm actually a data scientist. I built a well-documented notebook. Does that fit into nbmake?
Yeah, it does. Like, so if you're prototyping a model, for example, in trading firms, they will sort of prototype a trading strategy. They'll pull in some data. They'll try and make certain predictions, and they'll do that in a notebook before handing over to a quant dev. So a quant researcher, which is the data scientist in this use case, would write their model in a notebook. They'd hand it over to a dev. The dev would then reproduce their results before putting it into the trading system. That step of trying to reproduce a data scientist's results is always tricky, right? Because you've got to attach to a remote data source. You need the same dependencies in your environment, and the code's got to work at the end of the day. So putting in testing, at that boundary where the quant researcher hands over to the quant dev is really quite powerful.
So actually, this is a good tie-in into the larger question of, you've got software engineering, which is, a lot older than building ML and AI models that get deployed into production. So software engineering has a certain workflow and best practices that we've learned through years and years of implementation in rigor, right? So what lessons can we learn from software engineering? So if you look at, for example, Alex, the typical software engineering workflow, right? So a lot of these map into data science, right? So you will gather requirements. You might have a design phase. That I don't know if it maps into data science where you're wireframing, right? So then you implement, then you test. And testing can be unit testing, integration testing, functional testing. Then you deploy. Then you have monitoring and observability. So a lot of it could translate into machine learning, right? So of course, machine learning now involves data and model and is probabilistic. So let's take one area in particular, testing. What's your take on so can we map unit testing, integration testing, and functional testing into ML?
Yeah, I think so. I don't generally feel like ML is so different that we've got to rewrite the rulebook for software engineering. But we do have to appreciate that the organizations that create, machine learning models are quite different in terms of the people, the skills, the background, and
the actors involved in their background. Yeah.
Yeah, exactly. So, all of those things you listed, integration testing, unit testing, etc., they're all just as necessary as before, but in certain cases, they're a lot more challenging, right?
And who's going to do that now?
Who's going to do that now? Well,
is the data scientist going to write their own unit tests?
To an extent, yep. Yeah. Even outside of machine learning nowadays, it's so common to have this pattern where you've got an application developer and then you've got a platform engineer. And the point is that the systems have become a lot more capable over the last 30 years, but they're also a lot more complex. And so you've got an application engineer who's really focused on the business use case. And then you've got the platform engineer that abstracts away all of the infrastructure they work in. And I think one of the main benefits of this pattern is that the application engineer has a simple enough environment that they can still test their own logic, but they need to make sure that they integrate well with the platform engineers under the hood. This is the same for machine learning, right? the challenge is that it's not always clear what the platform capability should be. And as a result, right now, there isn't a great boundary between what's a machine learning application and what's a machine learning platform. And I think that's why, it's not always reasonable to expect that there's the same level of testing because it's so complicated.
And so in your experience, so since you work with a lot of clients across many industries, what is the state of processes and the amount of rigor people put into developing and deploying ML today? I'm sure it varies and it's all over the place, but
yeah, it varies. Generally speaking, it's lagging behind web applications, and that's just purely because this is a newer style of software application that we're dealing with. The one thing I've noted a lot in the early warning system project is the amount of QA that's happening. If we still want to run machine learning systems in extremely critical environments, but because we don't have the same abilities to sort of test them and they're a lot more complex, similar to the early days of web applications, there's a lot more manual QA involved where people are constantly just, putting in hours operationally checking that the system is doing what it should be.
Yeah. And actually in AI and ML, there's this movement around what people are calling alignment, right? So making sure that the model is best practices for making sure the model is intended, is behaving in the way you intended it to behave. So then people are coming up with best practices there as well in terms of what should we be doing to test robustness, for example. So people are doing things like adversarial testing and adversarial training, right? So a lot of it too, Alex, I think is part of it is cultural and vocabulary, right? So the software people have a certain methodology and certain language that they use that the ML people have a completely different language, right?
Yeah, I think there's definitely a case of different words meaning the same thing. Working with data scientists, machine learning engineers, there's a lot higher sort of rate of people who have come out of PhDs and research environments. And so they tend to be a bit more mathematical with how they discuss things. So what we might call testing, they might call validation or calibration or something like that. But I think that there's a general need for putting the alignment question into the user experience. So one of the things that the early warning system has is like an explainability feature that tells the user, this prediction you're seeing is because of this data point. And I think that there's a lot of product questions being solved between engineers and data scientists there.
By the way, I don't know if I mentioned this to you in advance, but in some sense, the data engineers have been thinking about the same problem for a while too, right? Because they're tasked with building and maintaining data pipelines, and data pipelines are at the heart of many of these ML applications. And in fact, if you have an ML model and it starts kind of degrading in performance or behaving weirdly, chances are at the heart of it is some pipeline broken upstream, right? So in some ways, in many ways, the data engineering community has been thinking about this for a while too, right? So how do we inject more rigor into how we build these pipelines, right? Because in their case, the pipelines could run across multiple systems, multiple distributed systems, right? So how in the world am I going to do integration testing in that environment, right? So it's interesting that at least the right questions in my mind are being asked. What do you think?
Yeah, I agree. I mean, going to sort of current topic of interest, which is like ChatGPT and these large language models. Uh, I think that people want to be stopping faults early in the system, but we know that you can at best catch most faults, and a lot of faults will make it in front of the user. So every single product, with machine learning models in it right now, it needs to tolerate the fact that the user might say, "This doesn't make any sense. I need to report something's wrong here." Um, but yeah, it's definitely an issue where you can have a really simple problem in a source data set, and if you're fitting a model every day or on a regular basis, that uh, human error inputting a data point in a faraway system can result in bad predictions, and tracing the behavior in the model back to that like root cause is an unbelievably difficult problem, which is unsolved.
Yeah. And if you think about alignment and testing, right, and or alignment in general, right? So as you mentioned, human oversight and control, right? So being able, maybe some of these systems will still require having a human in the loop or having some human oversight, or at least gathering regular feedback from humans, right? Or in the case of these really large models, the fact that they're black boxes, to what extent can you provide some tooling for at least the people in charge of maintaining and deploying these models, some tooling around, I hesitate to use the word interpretability, but some sort of explainability so that they can diagnose at least what's going on with the system, right?
Yeah, I think that at the core of it, even if you can't say this is why you got this result in a satisfiable way, there has to be some method of running a counterfactual and saying, what if this had been different? Would we have got the same result? And that's kind of the best we've got right now. But as you were saying, um, there is a massive need for all of these systems to have human operators monitoring them. And I think alignment is perhaps something that I see as a bit philosophical, but the general idea of not fully understanding what the model is, uh, geared towards achieving. I think that is really why we need to have great human operators and operational processes around all of these systems.
Yeah. So a lot of these teams releasing these cutting edge language models do have alignment teams now. That's the good news. And so they do things like red teaming, for example, right? So where they have experts from, I don't know, security, cybersecurity, and purposely put these models through their paces, right? So I mean, so in many ways, the things that the cybersecurity folks do in regular software, penetration testing, these kinds of things need to be done for these models as well. By the way, so these large models, so nowadays, of course, transfer learning has become kind of a standard choice in many domains where people take advantage of these pre-trained models. Maybe you fine tune it a little bit, but largely you start with some kind of pre-trained model. So the question there is is there a different way for building these large models that kind of mimic how people build open source software more generally, right? So by this I mean you have collaboration, version control for models, and all of these things. So what's your sense of in terms of, as these models get more and more complex, it's kind of like uh, open source software has some pieces of open source software are also equally complex, even more complex than these models, but somehow people figured out a way to collaborate and build it out in the open, and basically through having more eyes, maybe the software becomes better.
Yeah, I think so for context, you shared with me a blog post
Yeah,
earlier
by
today.
Colin Raffle. Yeah, yeah, yeah.
Yeah, and the idea behind that was saying, what if you could take a foundation model and someone can solve a specific problem with it, and then merge that those changed weights back into the uh, um, model so that other people can benefit. Um, I see the problem there, and the problem is that we need to make sure that we can bring, the whole open source community's ability to improving these systems. I don't get the impression that that's the right way of going about it. I think that in many ways, the foundation model is an output, and we need to make sure that we're fixing the source of the issue. So to me, and by the way, this is it's a bit of a um, potentially a naive sort of beginner's view on this, but I would put more of an emphasis on collaborating on making good data sets.
Oh yeah, yeah,
And
yeah, yeah,
yeah,
yeah. But I guess the point of this, so set aside the data sets, right? So and then the fact that you have a pre-trained model. So granted, some of these models are ginormous that you know very few people maybe have the funding to actually train them from scratch. So if you're starting from kind of the pre-trained model, maybe you can still make a contribution without having to go through the training from scratch, I guess is my interpretation, right?
yeah, and I think the core thing you just raised there is the cost of training the model, right?
Yeah.
And anything that economizes that is the right way to go. So
Or
yeah,
the reality is because the cost is so high, most people actually start from the pre-trained model. So the reality is actually more like people are not training from scratch most of the time because it's expensive. So what do we do about that if that's the reality? All right. So
yeah, well, I really enjoyed the recent episode you had with on sky computing,
yeah.
and I think that to a great extent, giving people the ability to do more training for less money is really important, and I think it's extremely promising as well. Um, but there's also other ways of economically, sort of sharing contributions. I'm sure you're aware of like the Prompt Hub and other ways of people sharing sort of prompt engineering techniques. But yeah, it's really early days, and my gut feeling is that we're going to see the price coming down on assembling a lot of this technology.
Yeah, yeah, yeah. So one trend now, which is, the scaling laws still hold in the sense that, the larger the model, probably the better it is. But what people have found recently, starting with DeepMind last year with Chinchilla and this year with Facebook and Llama, is that you can take a moderately sized model and maybe saturate it more with more data during training, and you get just as good performance. So the funny thing about this is when people say moderately sized, it's still 7 billion parameters, but of course they're comparing to something that's 180 billion parameters, right? But the point is that people maybe we're still in the early days, and people might end up figuring out how to get by with models that are more reasonably sized, and in which case more people can participate in the training from scratch. If there's more learnings into how do you build good models if you have more data, but you saturate more during training. And if that's the case, maybe then uh, instead of taking these pre-trained models, people will start participating in the training from scratch phase, right?
Yeah, for sure.
Yeah, yeah, yeah. And so, what are you paying attention to now in general in the area of just software, ML, and AI?
Yeah, sure. I mean, obviously the big thing to be watching right now is the progression of deep learning models to these large language models. And
But you're
uh,
you're much more pragmatic about it, right? So in terms of you're not building the model from scratch, but what are the implications for you as someone who will help people deploy these models?
Yeah, well, of course, we primarily work with AI companies in the UK, and I think everyone right now is figuring out what are the products that are going to be built, for enterprises or for other large businesses that are going to leverage generative AI. They're going to be really different types of products to, the sort of recommendation engines, time series forecasting applications of the last 10, 15 years.
And what are, Alex, what are the implications for infrastructure?
Well, the implications are that we're already spending massive amounts of money on the cloud, and it's only going to get harder to keep costs under control. Security and privacy of an organization's data is already, a great concern. If you want to build an AI product and bring it to market, you're going to have to contend potentially with deploying it onto another company's cloud, having one deployment for every company, deploying it on-prem. And it's going to be extremely difficult when we move increasingly to non-tabular data due to the management costs of just moving it around. So yeah, we expect that things are going to get messier in terms of infrastructure. Cloud costs will go up, and we're going to have to find ways to economize.
Yeah, and I think one of the trends that I'm starting to sense is that more organizations and more companies than we think will end up actually building custom foundation models for a variety of reasons, right? So it might be because they're not comfortable sending their data to an API, or maybe they're not even allowed because they're in a regulated industry. Maybe they want to move faster than their competitors, right? And maybe there's security reasons. But, the trend that I raised earlier, which is maybe also we're getting to the point where they can get by with, I hate to use the word small if the model still has hundreds of millions of parameters. But in this world, maybe they can get by in the future. Maybe we can get by with smaller foundation models, in which case more people will end up building their own. Because otherwise, you're sending your data to an API, right? So
exactly, yeah. And I think most large organizations, they don't want to be dependent on OpenAI's managed services. I'm aware that I think Facebook's Llama model can now be downloaded and hosted, and as you said, it may be smaller than some of the large models, but it still takes in tens to hundreds of gigabytes of memory to host.
But one demonstration of the pace of change is that within weeks of release of Llama, people had it running on a laptop, on a Google Pixel phone, and even a Raspberry Pi. Yeah, so we need more of those types of models, but with the right open source license.
Yeah, the right license. Also, the right tools around it. A model is not a product, right? A model has some raw capabilities, but there's got to be. I think increasingly there's the need for reinforcement learning and human feedback and the right systems around it to make it actually valuable.
Right. And with that, thank you, Alex.